All right, I just want to welcome everybody to our virtual 2020 Plus Program Expo, and this is Data Plus Room 3. We are about to have a presentation from our last group before lunchtime, and this is the Forecasting Campus Energy Use Group with Grace Ann Llewellyn, Ethan Schwartzentruber, and Shota Takashima. And they're going to be talking about how they helped our facilities group optimize campus energy use using a forecasting application. So yeah, take it away, Ethan.
Sure. Does everybody see my screen okay?
Yeah, and feel free to zoom in on sections if you don't mind so we can see a little closer.
Sure, yeah. How's the font size right now?
You can go a little bigger, I think. Just
like
a touch. Yeah, that's
perfect. Or more
perfect.
zoomed out?
Great. That's great. Zoom in. That's perfect. Yeah.
Okay, awesome.
Thanks.
So to give you guys a general idea, so Duke Facilities manages a bunch of different types of utilities. And for this project, we focused on chilled water, steam, and hot water. And the data that we had is basically usage levels, usage measurements for those utilities across a bunch of different buildings, most if not all of the buildings on Duke's campus, typically at like a 15-minute level. And what we ended up doing is sort of building a tool for them to use. And their main application here is budgeting, right? Both budgeting for new buildings, so understanding what they need for a building before it's built, if they can, and then also forecasting the usage for current buildings so that they don't have something happen like, the worst case scenario would be an outage, right? Yeah, so there are kind of a few different steps, and we provided a tool for them to sort of run that flow themselves, right? So the data, sensor data in general, as with all data that has just been pulled out of the world, has a bunch of problems, a lot of different defects, blanks and wrong values and all kinds of things. And we did a bunch of work on data cleaning, and Grace is going to talk about that. And then we will get into the actual forecasting models. And then I will, at the risk of blowing up everything in front of everyone, I'll give like a live demo of the tool and show you guys where you can download it and play with it. Grace, do you want to jump into data cleaning?
Yeah, so for data cleaning, some of the data we were given was very messy for some of the buildings, where a lot of them had really large spikes, or they had, like in the visual, they had single data point spikes. And a lot of the buildings also had negative numbers too, which obviously were anomalous, so we would have to impute those immediately. We used 3 anomaly detection methods: the interquartile range method, the seasonal extreme studentized method, and the standard deviation method. The IQR method was just a simple method that calculated an upper and lower bound for the data, where the lower bound was normally negative. That was the same for the entire data set, as you can see in the visual, just one line. And it wasn't rolling, so it helped catch the large spikes with a lot of data points that might not be caught with the rolling method. The seasonal ESD method decomposed the data into its seasonal components and checked if the points in the residual were outside a certain number of standard deviations from the mean. The SD method put the data in windows and then determined if it was outside a certain number of standard deviations from the mean of that window. We then imputed the data by averaging the 10 nearest non-anomalous neighbors. Still, some buildings, even anomaly detection wouldn't help if the meter got turned off for a really long time, or if the energy data was just unusable, like the Allen building, which everything was a weird kind of like stair thing that really wouldn't make any sense for energy data, so we just couldn't look at that. So for our forecasting methods, we had 4 forecasting methods. One was a simple averaging, another was Halt Winters, another one was SREMA, and then the last one was CNN. For data forecasting, we required that the user give at least 2 years of data for each forecasting method. The simple averaging method we used as a baseline, and it took a naive average of the same month in previous years. So all of the Julys would be added together and then divided by the number of Julys. And then you would expect the next July to be that average that you had calculated. The Holt-Winters method used exponential smoothing, which meant that the observations would have an exponentially decreasing importance over time. And the next one is CNN showed, if you want to take it.
Yeah, so neural network model predicts the target month usage using the last 12 to 12 months of usage measurement before it. So in terms of predictive accuracy and computational load, so CNN is the best performer compared to other weak drive. So long-term short memory and GRU weak drive. So using randomized cross-validation, we tuned its hyperparameters, and using early stopping and making model checkpoint, we prevent overfitting during its training process. So compared to naive averaging model, Holt-Winter and CNN didn't perform well. Because of the lack of data, a more complex model like them tend to be overfitted. And so if we have sufficient data, they might be outperformed than the naive averaging method.
Yeah. So all of these cleaning tools and forecasting, as we looked at the data that they had and the purposes that they wanted and sort of where they wanted to go in the future, we found that there were some things that the facilities team wanted to do that involved data that they didn't really have yet, right? They wanted to do stuff with temperature normalization or normalize the usage for the number of people in a building at any given time. And so rather than just sort of write a paper and turn over like a set of predictions, right? Like here's the usage for the next 2 years for all these buildings, we decided to sort of give them something that would let them repeat it. And in the bottom right corner, you see a screenshot of that, and then I'll show it to you. But basically, we have a little web-based tool that runs in Jupyter where you can upload data, and at this repo at the bottom, you can try it. I have some sample data uploaded there. And anyway, you upload this data and you sort of choose the options that you want for data cleaning, and you can tune that a little bit. You pick a forecast model, and then basically you have a couple different options, right? You can graph your forecasts, or just sort of a data cleaning visualization similar to this one that shows you what's been weeded out so that you can get an idea of whether that's helping you or not. And then at the end of it, you can export that data to like a CSV so that you can, just so that they're not stuck with our visualizations, right? They can store those and do whatever math and whatever visualization they want to do with it. Do we have questions right now, or anything anybody wants to jump in with before we go into a demo, or not really? Doesn't sound like it. Okay, let me start it up. Give me a moment. There we go. So if I upload my sample data here, tell it that the frequency of my input data is 15-minute data, and I maybe turn on a couple of data cleaning options here. I'll just turn on all of them. Do a plot for that. I can see, it looks like it's maybe a little bit aggressive, cutting off some of the peak. That's probably not an anomaly. Takes out some low values that probably are an anomaly, unless maybe the building was shut down. But at the end of all this, we're doing our forecasting on the monthly level. So this is mostly just kind of adjusting it. It's not, the aggregation itself has kind of a smoothing effect too. And then if I plot the forecast, I can see that, and then I can also download that CSV. I'll create a link up here, and I can download that and feed it into whatever tool that I'm interested in. Yeah, that's it in a nutshell. If we want to open it up for questions or comments on either the poster or the demo or anything.
All right, well, I have a question. So based on what you guys were able to cover this summer, was there, were there like sort of actionable items that your client found they could do based on your discoveries?
Yeah. So when we got to the team, the sort of the current state was that forecasting was done mostly manually, right, by an analyst of theirs, and it was done with this approach, this average of previous years approach, but it was also done with a lot of manual adjustment, and they had other cleaning tools. And I think mostly we provided them a couple pieces of value here. And one was one was actually adding some features, right? We gave them some forecasting methods and some data cleaning methods that they didn't have before. And then the other was we sort of put the process in one place for them, I guess. They had sort of a bunch of different Excel files with a bunch of different scripts floating around, and they had like a data cleaning tool written in Tableau and things like that. And I think from talking to them, I think putting it all in like a web-based tool that they can just throw up on a VM somewhere and all get to and use is going to be useful for them, just for like repeatability and standardization going forward.
That's great. We've got a question from the audience. Andrew Patterson is asking, was there a challenge you faced that you did not anticipate or that took longer than you had thought, and how did you overcome it?
Let's see, let me think about that.
I would say with the anomaly detection, we really didn't think it would take us that long, but it ended up taking us a couple weeks to get through it all, just because some of the data was really messy and we were trying to find the best way to do it. And at first we were running it with 15-minute data, which just took forever with anomaly detection to do. But once we accumulated it to the daily level, which also helped with some of the anomalies, the data started looking much better.
Yeah, that's true.
If you had had a little more time on the project, say 3 or 4 more weeks, is there more you would have liked to have done with this?
Probably temperature normalization. We did get some temperature data. Essentially, it works pretty well for some buildings that have less messy data, and pretty poorly for some buildings that have, huge, 6-month wide backfills in the data or something like that. I think there are probably ways to deal with those, but it didn't quite get done.
Were there oh, sorry, go ahead.
I was just gonna say another thing that I probably would have changed was the data imputation, because it was just averaging the 10 nearest neighbors that were non-anomalous, but we had some stretches that were like a couple months of just like negative numbers or really high numbers that we knew were anomalies. So when it's trying to average the 10 nearest neighbors that weren't anomalous, it's going pretty far to find those 10 nearest neighbors, because most of its neighbors were anomalies.
Yeah, that's interesting. I mean, how do you resolve anomalies, like, in order to get sort of a clean report? I mean, for somebody like me who's actually not a data science person, it seems to me like that's an interesting conundrum for you to work through.
What do you mean by how we resolve them? Like how?
Yeah,
how
well, like, so I guess my understanding, like when you're looking at the average for a building's use and your data is not quite, I don't know, accurate, I suppose, how do you resolve in order to get like a picture that does appear to be a little more accurate? And then, yes, Jason, we will let you go ahead and talk for your question.
So long story short, it depends on what's actually wrong with it, right? So we have blanks where there's no value, and for that we sort of so generally you need 2 strategies, right? You need to detect problems, and you need a strategy for what's going to go in place of those problematic values.
Yeah, I think that's kind of what I'm asking, like that gap where there's not,
right. And so
information.
Our strategy was to take the 10 nearest points, like in time, right? So like the 5 on this side, 5 on that side, if excluding other values that we didn't, that according to our like mathematical definition of an anomaly were not also problematic values, and average those and replace the point with that.
Gotcha. Okay. Yeah. All right, Jason Elliott has a question and he would like to ask in person. Go ahead, Jason.
Thank you. So I work in Sustainable Duke, and part of our work this past year is working with the Basque Connection on developing energy reports for buildings. And then COVID hit, and energy reports now are going to be really hard to use the past 6 months of data to interpret what will happen in the future. So how is your group taking this anomalous data and interpreting that going forward?
So that, so our current strategy is to just chop it off and ignore it, right? And essentially to say, if you really want good predictions, you're going to have to wait until you have more non-COVID data. The strategy that we would have liked to have, but did not have the data to execute, is so we can't prove this because we don't have the data, but in theory, the two biggest factors are like temperature and the number and the building usage, right? And COVID affects one of those and not the other, right? It doesn't really affect the outside temperature at all, and then it affects the usage of the buildings a lot. And one of the things that OIT and facilities were interested in doing was normalizing these predictions for both of those things. So trying to remove the component of temperature, which, like I mentioned before, we kind of got close and didn't quite get into the final product. And then the other one, we didn't really try at all because we didn't have data, but they're looking to collect data on the building's usage using Wi-Fi access points. So just look for the number of devices and then sort of like deduplicate them by the net ID that they're using, right? So that my phone and my laptop don't count as two people because they're both Ethan's net ID, right? And then basically using like a linear regression, subtract that from the series, and then essentially you can add it back in with however many people are supposed to be there to sort of like renormalize your COVID time data that where nobody's in the building. Does that make sense?
Yeah, yeah, definitely. Yeah, we, for the Basque Connections project, used Wi-Fi data. It's very fascinating. It's not perfect. You have data cleaning in every data set that you're going to get, but it's definitely really useful. My second question is, it sounds like you're doing this building by building. What interpretations can you draw for an entire campus or potentially a new building that's going to be constructed? Can this help inform potential energy use in a new building before it's constructed?
Yeah, so I guess I'll have to make like a stipulation at first to say everything so we didn't use energy data, we used steam, chilled water, and hot water. So it's always possible that it just doesn't work the same way. But in general, I think, again, if we posit that the temperature will be the same and the usage will be the same, we can see a lot of the different patterns. For a while, we played with trying to do like a regression-based model with a bunch of different factors like what type of building it is and how many people are normally in it and the size of the building to try to sort of determine like a similarity between buildings. But I think basically it just turned out that the stakeholders were more interested in forecasting for the buildings that existed, I think.
Great, thank you.
Yeah.
Yeah, I would say like, because Duke campus has like these remarkably new and efficient buildings, and then we also have these ancient buildings from the 30s, you know, like I used to work in the Allen building, you know, and you were talking about how messy the data was from there. And I could only imagine based on living there or working there and having, you know, dealing with the heating and cooling issues of that building, like, I think it would be really hard to average for the whole campus in a good way because of just the age of different buildings on campus and how their energy use is. Like, is that at all something you got granular about, or?
I remember having conversations about it. It's not something that like our model quantitatively considers, if that's what you're asking.
Okay, yeah.
And we never got the chance to run average type of stuff for the overall campus to get like for this type of like if this is owned, all the buildings owned by OIT, these have this average amount of energy. So we never did get the chance to do that because we were focusing more on making sure the forecasting methods work better, and FMD didn't really have a need for us to be doing that as much.
Interesting. Okay. Well, this is really great. Do we have any other questions from the audience? All right.
Okay,
Well, we are at time.
stop the share.
Yeah. Really appreciate everybody's attendance and work this summer. You guys did some really exceptional work, and under some pretty unusual circumstances as well. So thank you for being part of the great experiment this summer.
Thanks. It's been fun.
Yeah, please do check out the other rooms today. Yeah, we have some more sessions running this afternoon as well after lunch. So yeah, thank you very much.
Thank you.
Bye-bye.
All right. See ya.